In this section, we're going to concentrate on the term tonicity. And when we're talking about tonicity, we're talking about the concentration differences between one environment and another. So often we'll be talking about the tonicity of the solution outside of the cell or the extracellular environment. And we'll be giving them names compared to if that solution is more concentrated or less concentrated, or the same as that solution inside the cell. To do that, though, I kind of want to give you some background on what the plasma concentration is in our blood. And that osmolality is 0.3, or so I'll say blood plasma equals 0.3 molality, or we can say that's the same thing as 0.3 osmoles, or it's the same thing as saying it's 300 milliosmoles. So you're going to see those terms used a lot. And what this slide is showing you is that a 0.3 molal solution of glucose is going to be the same as that we're going to find in the blood plasma, 0.3 mole solution. And we also know that with sodium chloride, because that's an ion that dissociates, it's only going to take a 0.15 molal solution of sodium chloride to have the same osmolality as that in the blood, because that's going to double, and that's going to be 0.3 when you add them together. So these solutions are all considered to be isoosmotic. Iso means equal, and we're talking about the osmotic pressure. So they're going to be the same concentrations, if you think about it, as blood plasma. Now, you've probably seen them more as normal saline being called 0.9%. And that's going to be isoosmotic to the blood. When we put in normal saline, that's the concentration that it's going to be. So I would want you to derive and understand, well, how do we know that that's the same thing as 0.3 moles? I'll show you how to do that here, and then I'm going to want you to do that for the 5% dextrose. So if we were going to take a 0.9%, that's the same thing as 0.9 grams of sodium chloride per 100 milliliters of water. So I'm just going to write this down here. 0.9 grams of NaCl per 100 milliliters of water. Now we can factor this down. So if we know that we want to get, if we know that our osmolality is measured in moles per liter of solvent or kilogram of solvent, we know that we've got to change this milliliters to liters. So we'll say times 1,000 milliliters per liter. And if we wanted to, we could even convert liters to kilograms, because we know that there's 1 liter per 1 kilogram. And this is all of water. And then we know that there's 1 mole of sodium chloride per 58.4 grams, or 58.44 grams of sodium chloride per mole. So you can write that either way, and since we're going to want to cancel out these grams over here, I'll put the moles on top. So we'll get 1 mole of sodium chloride per 58.44 grams of sodium chloride. And we also know, so now we know that these grams are going to cancel out with these grams. And we already canceled out the liters and the milliliters. So now, right now we're dealing with moles per kilogram. And we know that there are 2 osmoles per 1 mole of sodium chloride. Because remember, that's how that thing dissociates. So when you multiply this whole thing out, you're going to end up with 0.3 osmoles, which is exactly what we were looking for up here. That's the same thing as 300 milliosmoles. So you should be able to do the same thing with glucose. Start with your 5 grams per 100 milliliters and work your way through. And you're going to have to really concentrate on the molecular weight and the osmoles per mole, and then you should be good. So when we look at tonicity then, tonicity is the effect of that solute concentration on the osmosis of water. So we're looking at how that concentration is going to change the pull of the water. We know that if a membrane separates a 3 mole glucose solution and a 0.15 sodium chloride solution, there will be no net movement of water because they both have the same number of osmoles in it. So water won't change. If we have a solution, so here's our cell here, and we have a bunch of solutes in a cell, and we have, you notice, a lot less solutes outside of the cell, we're going to call that hypotonic because it's in regards to the number of solutes outside compared to inside. So in that case, water is going to enter the cell because water is going to follow the solutes, or water follows the salts. In that case, what's going to happen is that if water's coming into the cell, that cell is going to swell and it could eventually burst, or the fancy name that we give that is lyse, L-Y-S-E. The opposite side of that is if you have a bunch of solutes outside of this cell in the external environment, in the external cellular fluid, and compared to the number of solutes inside the cell. In that case, the water is going to follow the solutes and go outside of the cell, and it'll cause that cell to shrink or to shrivel up. And the fancy name that we call that is crenate or crenation. So we can kind of look at a red blood cell here, and if we put that red blood cell in 3 different types of environments, we're going to see 3 different things happen. If it's in an isotonic environment, nothing's going to happen because we're going to have no net diffusion. The amount of water going into the cell is the same as the amount going out, so that cell size is not going to change. If we're in a hypotonic solution, so we've got very few solutes outside here compared to inside, then water's going to come into the cell. That would be hypotonic, and hypertonic would be is if that water's leaving the cell and it's going to crenate. I'm going to show you just a few other examples. So here we've got an isotonic solution. Again, no net movement of water. Water's going in and out, but no change overall. So the inside concentration is equal to the outside. Then we've got a hypotonic, and you can see that the water is going to come in because there are fewer molecules outside than inside. And these drawings don't show the inside, so I'm going to show you that on the next slide. In this case, the cell is going to swell or burst. And then the last one, hypertonic, you've got a ton of solutes outside compared to the inside, so the water moves out, and that cell is going to shrink. Here's the way that I kind of prefer to see it. All the greens are solutes, so I put some inside as well as outside. You can see here they're the same amount, so you got the same amount of water going in and out. That's isotonic. If you have fewer outside compared to inside, those water molecules are going to move into the cell, cause that cell to swell or burst or lyse. And then if it's hypertonic, you can see that the water is going to move out of the cell, causing that cell to shrink because it's going to where all those solutes are. So let's go through a little flow chart that kind of put this in a real world perspective. If we're looking at somebody who's getting dehydrated, what's really going on here? Remember, if we have our sensors, integrating sensors, and effectors, they're all going to be having an interplay in what's happening. So when you have somebody who's getting dehydrated, they're having water loss, and that you can have that from excess sweating or urination. So when that happens, you're going to have a decrease in blood volume. If you decrease the water in that blood plasma, what you're really doing is you're increasing the osmolality, because now you've got less liquid, less solvent, because water is our solvent and we're losing the water. So even if we have the same number of solutes in there, because there's less solvent, the osmolality, or the concentration of what's left, is going to increase. That's a really big concept to get here. So with dehydration, we're seeing an increase in plasma osmolality. Well, that's going to go that blood plasma is going to get detected by the osmoreceptors in the hypothalamus. Remember, we had a similar slide on the first day of class. We said it's going to the hypothalamus. Well, now it's osmoreceptors, so they're detecting the osmolality in the blood. Those osmoreceptors are going to send off signals to have us do two things. One, it's going to make you thirsty, so you're going to drink more and get more fluid into your body. The other thing it's going to do is it's going to kick off a chemical or a hormone called antidiuretic hormone. And when that gets secreted from the posterior pituitary gland, it's going to go to the kidneys and result in reabsorbing more water back into your system, or it actually prevents water from escaping in your urine. And all that is going to, between those two, increase thirst and ADH. It's going to increase your water intake and your water retention. And because of that, we're going to have a negative feedback loop that comes back, and it's going to reduce our blood plasma osmolality to get us back down to our baseline where we want to be, which should be about 0.3 osmoles. That's the goal. So now, I want you to imagine this. Imagine that there's an erythrocyte, a red blood cell, and we know that in that blood cell there's a lot of solutes, of which one of the components is urea. A very small component of this is urea. We know that the osmolality of that internal environment of that cell is 300 milliosmoles, or 0.3 osmoles. So now I want you to take this cell and I want you to put it in a solution that contains only urea. So if we take this, we say that here's a beaker, and in this beaker we're going to have a red blood cell that we know is 0.3 osmoles, and we put it in a solution that contains urea out here, and this urea is exactly 0.3 osmoles of urea. Okay, and that's all that this solution is, just urea and water. So now, consider that this membrane here is permeable to urea. So urea can either go in or out of that membrane, and so can water. But let's say nothing else. What's going to happen to this cell? Knowing everything that you've learned about osmosis and diffusion, and I want you, it's going to be a couple-step process, but tell me what's going to happen to that cell, and we'll talk about that in class as well.